Right, next topic we're going on to is circle theorems, and I'm not a mad fan of the order that the book delivers the various bits of knowledge about this particular topic. So I am going to do a proof with you which will allow you to see where all the circle theorems come from. This is a particularly important proof, and I think it should be the start point for this topic. Kit you'll need for today's lesson: you're going to need a pencil, a ruler, some pens, helps if you've got a few different colours, and of course, all important for circle work, a pair of compasses. No comments about my compass, please. I had to nick it off my daughter. Right, so job number 1, draw a circle. A decent sized circle will make labelling this diagram significantly easier, so try and make it about as big as you can realistically draw and fit on the page. And a useful tip here, if you're not good at drawing circles, is to turn the book and not the compasses. There we go. Try and stay on camera. There we go, look at that. That's marvellous, marvellous. And make sure that the centre of the circle is labelled. Now then, I'm going to choose 3 points around the circle, and I'm going to try and choose them in such a way that there's no implied symmetry or special positioning of these points. So I'm going to pick a point up here, a point over here, and a point over here like this. I'm going to join them up as follows. Top point to the right, top point to the left, and then join the bottom of both of these points to the middle of the circle. So far so good. And then we're going to draw from this point here through the centre of the circle just enough to divide this angle. This is the centre of the circle. I'm not going to label it with anything because there's going to be various bits of angles I want to label around here, and I don't really want to confuse that. This is point A. We'll call this B, and we'll call this C. Now then, this is where it gets a bit technical. For reasons that will become clear as this proof progresses, I'm going to label this angle in here as 2 lots of x. Now, that means that I can calculate this angle here by using the property of angles on a straight line adding up to 180 degrees. And that means that this angle in here must be 180 minus 2x. Focus only on the triangle AB to the centre here. Forget this side. Just look at this bit over here for a bit, right? Now the next observation I'm going to make is that the centre of the circle to A and to B and to C, those straight lines are all radii, which means they're all equal length. I can mark them like that to indicate that. I also know how to find the missing angles in an isosceles triangle when I'm given the angle that's on its own. I just need to do 180, take away whatever that bit's worth, and then divide it by 2. Because remember, both of these two angles here, they're going to be equal because it's an isosceles triangle. And how do we work this out? Well, I need to do, like I said, 180, take away whatever this bit's worth, and I'm going to have to half that result. And that will give me that angle in there and that angle in there. So let's process this and be careful of the minus sign. 180 take away 180. But then minus of minus 2x, I'll be adding 2x because when you subtract a negative you have to add it back on. All over 2. And then the 180 take away 180, well, that kind of, they cancel each other out. So all I've got is 2x divided by the 2, which is just x. So both of these angles here are angle x. Now, I could do a very similar explanation for the right hand side of the triangle. Let's call this angle 2y. That makes this angle here 180 minus 2y, and the reasoning would be exactly the same to show that these two angles are both a y. So, what is the significance of that? Well, if we focus on two particular aspects of this diagram, namely the angle B to A to C, that's all of this bit up here, and if we focus, I'm going to label this the centre now, O. If we focus on BOC, then what we can see is that angle BAC is equal to angle X plus Y. And angle BOC is 2x plus 2y, which is the same as 2 lots of x plus y, which is the same as 2 lots of BAC. So what we've shown with this proof is that this angle here is half as big as this angle here in the centre. So I'm just going to draw another little diagram down here as a little summary of that. These are quality compasses, this. My daughter is definitely not getting this back. Okay. Where's my ruler? Okay, and so let's just quickly replicate this diagram, but without all the calculation parts in it. So if we were to call this angle here theta, egg with a belt, Greek letter theta, and bear in mind this is the centre of the circle, then this angle here is 2 lots of theta, because the angle at the centre is twice the angle at the circumference for points that stand on the same arc in the same segment. So if you imagine these 2 points here, that's B and C effectively, B and C, and you're considering this bit of the diagram here, this angle at the centre is twice as big as this angle at the circumference. And I could move these points around and this would still be true, because I wasn't particular about where I chose A, B and C. I've just picked them around the circumference. If you were to move C or move B, the algebra of how we calculated these bits of information wouldn't change. So this is a very important circle theorem. Let's just put some words to this. Angle at the centre is twice the, I hope you can read my joined up writing, is twice the angle at the circumference. Looks about right. So the next thing to do then is to think about how this particular proof can be modified to give us some other general results. So let's draw another circle, just a medium circle this time. There we go. So here's B, here's C. Here's my angle 2 theta in the middle. And this is the first sort of important observation here. It doesn't really matter where I put A. So I could put A here, or here, or even over here. And I'm going to use some colour here this time. So let's label this one in black like this. Or I could label this one here like this. Or I could label this one over here like this. And each of these angles still meets the criteria whereby I've got the angle at the circumference must be half as big as the angle at the centre. So all of these angles here must be an angle theta. And so if I redraw this diagram but just forget about labelling the middle of the circle, I've got enough room there, I think I have, yeah. Let's just bring it up here a bit so you can see it. I am loving this compass. Hey. Then if you pick 2 points on the circumference, then what we say is that any angle that stands on the arc BC in the same segment do one more. Oops, overshot the wrong way. These angles here, they all stand on BC, they stand on the same arc, and all these angles are in the same segment. Remember, a segment is when you divide up the circle using a chord, which is any straight line that passes through the circle. So if I chop the circle and just focus on the bit that's above the pencil here, these 3 angles all stand on the arc BC, and these angles at the circumference, these are all equal. These are all, call it theta if you like. Okay, so that's one of the first knock-on formulas that comes from this this proof. Now, the second useful one. The second useful one is a sort of a special case of angle at the centre versus angle at the circumference. And in this instance, I am going to be particular about where I put my 2 points. So let's call this P and Q. And this time P and Q have been chosen in such a way that PQ is actually a diameter. Okay, so PQ is a diameter. And because PQ is a diameter, that's going to have an implication. So let's say I choose one of my points of A to be here. You can possibly just about see what's going to happen. So let's call that A. Or I could also do the point over here, I suppose. Like that. Or I could do one over here. So the angle at the centre this time, because this PQ is a diameter, let's label this O as the centre of the circle. That means that the angle POQ must be 180 degrees. And the knock-on effect of that is that all of these angles that stand on the arc PQ in the same segment, they must all be 90 degrees. They're all right angles. So this is a special case of angle at the centre, angle at the circumference proof, where PQ is a diameter, and that means that within a semicircle, the angle at the circumference is a right angle. It's 90 degrees. Okay. Now then, let's just draw a second diagram, just to show that. Okay, that's not good. Get back in. There we go. There we go, good recovery. Let's just draw one like that this time. Let's just put some words on this. Angle in a semicircle equals 90 degrees. Right, I think we've got room, if I squeeze it in, room for one more knock-on effect, one more proof that can be used from this diagram. So we need one more circle. Well, we're going to need two, but we'll get one more on here. Start about there. Right. So, need a bit of colour for this one. So where's he going with this? What's this all about? So, you've got to be a bit clever about how you view this diagram. So what we've got here is A, B, C, D. And the shape ABCD is what's known as a cyclic quadrilateral. That's because it's got four straight sides and all the points on the quadrilateral lie on the circumference of this circle. So first of all, I want you to view the diagram this way. And what we have is that if I call this angle here 2x, then this angle is x, using our rule that the angle at the circumference is half as big as the one in the middle. And then I want you to view the diagram this way round. Okay? And this time, thinking about the angle in the centre being that bit there, this angle will be twice as big as this angle here. In fact, if I use some clever sort of arc coding system here, it's almost implied. Let's label it the right way up. So I can call this angle in here 2y, and that would make this angle here y. Now, focusing on the middle of the circle, I know that the angles around a point add up to 360. So 2x plus 2y must equal 360. So 2 lots of x plus y is equal to 360. And if I divide by 2, that means that x plus y must equal 180. And this is the icing on the cake of this particular little bit of proof. What I've shown here is that the opposite angles in a cyclic quadrilateral sum to 180 degrees. So, opposite angles in a cyclic quadrilateral lateral. Sum to 180 degrees. Okay, very quick recap. Started with a big circle, angle at the circumference, angle at the centre. Some clever angle algebra and deduction led us to angle at the centre is twice as big as the angle at the circumference for the angles that are in the same segment. And then we used some special cases of that to show, first of all, that all angles that stand on the same arc in the same segment are equal. There's no writing there, is there? Angles standing on the same arc in the segment. Alright, angles standing on the same arc in the same segment are equal. And then we tweaked the diagrams so that the 2 points here allowed us to have a straight line passing through the centre of the circle, which is a diameter, and so angles that stand on that arc become half of 180, i.e. 90. Angles in a semicircle, 90 degrees. And then the third variation of this was to basically look at a cyclic quadrilateral and then look at the angle at the centre and how it related to the angle at the circumference relatively in each case, and from that we deduced that the opposite angles in a cyclic quadrilateral sum to 180 degrees. And I think that covers most of the covers most of the circle theorems that you'll need at this stage. There is one more nasty theorem called the alternate segment theorem, which we won't cover yet. That's for another time. Ironically, it's always the one that comes up in exams, but there you go. Hopefully that will help you get through the next block of questions. Thank you very much.